All right, problem number 4905, one more problem for today. So we are given an orthonormal basis. Here is the orthonormal basis. I'm going to designate this as S, Vi, such that Vi, Vj equals Kronecker symbols. Okay, so what else are we given? Oh, so we need to prove a couple of things. The first thing that we have to prove is that let's prove the fact that our how's it called? Okay, so the sum of this, the inner product of sums, Ui. Okay, I'm gonna designate this Fvi, and the sum of Bi Vi equals essentially to API's. So I mean that's pretty much simple. That's like one-step proof. All we have to do is just, we know that this is inner product with respect to orthonormal basis, which gives us a lot, because now we can rewrite this expression as, well, simply AI inner product, Vi sum, and there is another sum Bi Vi. By definition of inner product with respect to orthonormal Euclidean space, where I belongs to indexing set I, which can be written as the sum, and then there is another sum, inner product, AI, Bj, inner product AI, not AI, Vi and Vj, and here's AI, J and J, J upper J, and then we have the index, the sum with respect to its indexes, AI, Bj, and we have to keep in mind that this is the conjugate value here. And then Kronecker symbols by definition of our, orthonormal basis, which results in A equals J, because otherwise it would annihilate. And only what we have left here is AI and Bi, essentially conjugate value, which is exactly same thing as AI in I upper, AI, Bi, conjugate value. Here it is here. That's basically all the proof. That's all we need to do here. The second proof is a little bit more trickier. We are given the matrix B, which is Bi and J, and this matrix is said to be representing the linear operator T with respect to this orthonormal basis S. And then we have to prove that therefore, right, if therefore our Bij equals to inner product of T, or is that Vi, Vj. Yep. So how to prove this? What is the matrix B? Matrix B is the representation of Ts, which is T of V1 with respect to S, and then T with respect to TV2 with respect to S until TVn with respect to S. This is a definition of this matrix. So if we try to, well, let's say find TV I, and then this is the element Bij in this matrix is essentially the T Vi, and then so this is J, so this designates the column, and it's like the element of its vector, right? So this is the element of this vector S, J. And also at the same time we can actually see that, hold on a second, I'm gonna remove that because we can even simplify this. We can simplify that much more significantly here. We can write TVI as the sum because it can be represented with respect to this orthonormal basis. It can be the sum of, let's say, BI, this is I, J, and vectors V, right? From 1 until the n. Because this is exactly these values. This is exactly how it is represented. Because we know that TVI is just a matrix, it's just vector column B. Well, let's say I1, B, I2, right? BI, and transpose. And then our inner product becomes the sum of Bij, Vj, Vj, which is the sum of Bi, Vj, Vj, Bij, j from 1 until n, which is the sum of Bij, Kronecker, Ij, j from 1 till n, which annihilates for almost all values except the case when I equals j. When I equals j, that becomes identical to Bi, or Bij in other words. When I equals j, this is the same thing. So that should be it. So that should be the whole proof behind this problem, I guess. This is a pretty simple one.